My name is Derek Booth. I'm going to assume that I have been introduced, and we are just going to get started. Um, and I want to talk today about watershed context. Uh, I have worked in urban streams for a very long time, but I find my view and vision drawn generally to the watershed that surrounds it. And so what I'd like to do by way of organization for this talk is walk through these five elements one by one. So we'll start with really the purpose for this talk and why I think this is a useful way of thinking about and structuring our approach to urban streams. Is really to appreciate temporal and spatial contexts. By temporal, I mean the evolution of streams over time, and by spatial context, I simply mean the uh, differences in watershed settings in which we find these streams. And I think this is important because as we look around the landscape, we get a lot of urban streams. And, you know, they are really different. Um, and so in my judgment of this, urban stream restoration probably shouldn't mean the same thing everywhere, and it probably shouldn't proceed in the same way everywhere. So let's start with just some assumptions that I think we all have, or at least that I bring, and I suspect many of you will feel very much the same way. And I want to do this just by some field examples. This is a study that I and others had done for a couple of decades in Western Washington. In these next couple of slides, you always want to keep an eye on the tape, which is stretched across the channel, and you can kind of see faintly going across the top of this urban channel that obviously has been rather severely degraded. There's the same tape. The floor of the channel has actually dropped several feet in the intervening 3 years. And then here we are in 2008. It's actually dropped a little more. There's that same tape in the same location. Here's some cross sections that have drawn over it, and you know, we see deepening of this channel during a period of upstream urbanization. We see widening of this channel during a period of upstream urbanization. And you know, it comes as no particular shock or surprise that you put more water in channels, they get bigger. And in fact, it's true that many streams in urban settings respond similarly, of which incision in this example is probably one of the most common, despite what I argued just a few moments ago, namely that watershed settings are different, and those really ought to impose some fairly fundamental differences on the responses. So I think it's worth asking the question, why, not why are streams different, but actually why do they respond similarly? And I would suggest that that's because, you know, we may start with a landscape that looks like this. We may start with a landscape that looks like this, and they're really different, one from another. But by the time we are done urbanizing them, much of what makes them different, you know, it just isn't there anymore. So we could talk about differences in soil permeability or water holding capacity, but you know, in many cases, it's not a question of modifying those properties. That soil is just gone. This is an example of a subdivision under construction. And you see the last lonely remnants of the original ground surface. And all the rest has been either removed altogether or so completely compacted and ultimately covered with impervious surfaces that any initial intrinsic differences really may not make any difference. And then finally, we can just look at a fully developed landscape and appreciate that except for the variety in what's coming out of the sky by way of regional climate, really the differences are largely gone. And so I would argue that even as we behold an almost infinite variety of watersheds, um, we also can see that urbanization is really a very homogenizing influence. And as we look around urban landscapes, I think we can see both the evidence of differences, but also very much the evidence of homogenization. Uh, so to me, this is kind of the challenge that I would like to take on, although I promise you I will not actually resolve it all today, of how to reconcile this equalizing or homogenizing effects of urbanization with the variety that we see across streams and watersheds, both regionally, continentally, and globally. So with that as a preamble, if you will, let's start by looking at channel evolution and the what I call the temporal dimension of context here. So I'll what I'm sure is merely remind nearly all of you of what I think of as the classic channel evolution model, and whether you like the Simon and Hupp version or the Watson Shum version, very similar. All of them anticipate the same basic sequence. We add water into a channel or increase the gradient of it. The initial response is the channel bed declines, the stage 2. As the bed continues to insize, eventually the banks are oversteepened. We start to have widening through bank failure, and then eventually some of that, or enough of that, extra sediment being contributed by mass failures on the banks is re-equilibrated, leading to a channel that's ultimately somewhat deeper but not as deep, somewhat wider, and in a perfect world stabilizes into a new equilibrium form. So there's lots of examples of this, and I wanted to show you a couple from that same study in the Pacific Northwest, actually just one of those. So here we are in a channel that we visited over a 20-year period. And as we look at this, we can first recognize a first early stage of channel incision, of deepening of the channel, just like the classic model predicts. We then see over a period of years that as that channel deepens, it then begins to experience bank failure as well. There's actually a period where we have both expansion and both deepening and widening. And then finally, after a decade or so of those types of changes, in fact, we have a fairly substantial degree of channel infilling and a return not to its equilibrium bed elevation, but something that at least begins to return. And if we now just look at some field photos, here we are in 1997, which is after much of the degradation of the bed. This is where the bed originally had been 9 years earlier and the amount that it had declined. Once again, keep an eye on the tape. It's in the same place. So we come back 11 years later, and in fact, you can see both visually not only the change in bed elevation, the aggradation in bed elevation, but the commensurate stabilization of the channel margins as well, courtesy of the lush vegetation of the Pacific Northwest. So I would ask the question, though, what's wrong with the classic channel evolution model? Why can't we just use it throughout our kind of consideration of channel evolution, not only in the original locations that it was developed, but also in our urban settings? And I'd suggest that there are maybe three broad reasons why the classic channel evolution model may not be ideally suited for wholesale application, or at least non-critical application to urban channels. First off, we can have other disturbances. It's not just increases in discharge, although certainly in my experience, and I suspect that of most of you, increases in runoff is probably the single most common condition of an urban watershed. The classic channel evolution model is unquestionably both developed and displayed and applied on single thread channels, and actually not all channels are single threaded. Finally, not every urban channel is fully unconstrained. In fact, many of them are not, and it's important to understand how the imposition of either lateral or vertical constraints might affect that evolutionary trajectory. So let's walk through those three, we'll say, complications or considerations one by one. So first of all, other disturbances. One of the other disturbances that was listed on the previous slide is just what about channels that are naturally high sediment load? How are they going to respond to urbanization of a watershed? And in fact, although they are likely to have an increase in discharge, they're also quite likely to have much of their sediment load stripped out. And in regions without a high sediment load to begin with, like, for example, the well-vegetated Pacific Northwest, a reduction of what is already a low load may not be a particularly significant maladjustment of the fluvial system, and completely masked by increases in discharge. But there are regions of the world, and where I sit now in Southern California is one of them, where in fact watersheds have tremendously high sediment loads, and the channels have equilibrated their form and behavior in response to that, and a substantial reduction in that sediment load, for which our region's system of debris basins, as well as simply the paving and armoring of the channel banks, are really quite effective, can have impacts on the channel form quite independent of, and in many cases of greater magnitude than simply the changes in discharge itself. And again, because they tend to work, if you will, pushing a channel in the same disequilibrium direction, it can be actually very difficult to untangle, and certainly in a quantitative way untangle, the relative effects of increased discharge and decreased sediment load on the final channel morphology. Okay, what about the plan form? I've become more appreciative over time about how much we all bring our assumption of what a stream channel should look like. And I think the more you appreciate your own biases or expectations, the more you begin to understand how you are thinking about this amazing variety that we actually have in the landscape, and try and fit it into a few categories. I suspect that my expectation of what streams look like, since I grew up in a city, were formed by Walt Disney. And so I offer to you a Disney channel as at least my paradigm, but I suspect many of your paradigms as well for what a stream channel should look like. But in fact, well, I'd say, and in fact, many of them do. I mean, some of them look a little more complicated. This is a particularly cool example of one up on the Kenai Peninsula of Alaska. Sinuous, meandering, to be sure. But it is worth noting that many channels are not single thread, and in fact, as near as one can tell, they have never been single thread, and they are trained into single threadedness only at substantial loss of their ecological benefits as well as just morphological character. And indeed, many of these non-single threaded braided channels actually seem to be doing quite well, thank you, despite the fact that they do not meet a common paradigm for what a channel should look like. Now, obviously I'm not the first person to have noted this or figured this out, and I do call the attention of those of you who work in non-single threaded channel domains. A couple of papers that have begun to tackle this issue explicitly. Bob Hawley looking in Southern California, and Corin Thorne thinking a little more carefully about the ecological consequences of multi-thread channels and the evolution that we commonly see through a phase and sometimes ending at a phase of single thread channels. And the third of those other considerations that are, I would suggest, missing from the classic channel evolution model and that are not, or that render it not entirely applicable to an urban setting, is just the commonality of lateral or vertical, or in many cases lateral and vertical constraints of urban channels, which can't help but affect their evolution and their development. In fact, that's typically the point of these lateral or vertical constraints. And so we see rock walls, and whether or not we actually pave the bottom of the channel, the frequent interruption of the channel grade by hard points, culverts, bridges, and the like, tend to impose some constraints on temporal adjustment that really are not well considered or acknowledged in the channel evolution model. So I would suggest that there is probably some value, if only as a useful organizing principle, for developing or characterizing. I call it universal, but it's really only universal within the rather narrow universe of urban channels. But within that narrow universe of urban channels, I think we probably might benefit in, if only communicating to others outside of our field, if not in organizing our own thinking, about the range of conditions and the range of disturbances that we tend to see that are common to, if not unique to, the urban environment. So I would suggest that a fundamental division on whether or not the channel is actually capable of responding is fundamental. It's important, or at least it's relevant in any watershed context, but we bump up against this condition, the condition of non-alluvial banks or beds, much more commonly in an urban setting, and it takes us in very different directions. I'd also suggest that really formalizing our recognition that not every channel is single thread, and that both the responses may be different to disturbance, and ultimately the way in which we think about and approach restoration opportunities probably ought to be different as well. And then lastly, not every disturbance of an urban channel is associated with an increase in discharge, as is presumed by the classic channel evolution model. But I hasten to add that if you had to pick the most common, it would still be an increase in discharge. And so there are still many, many settings, including the example I showed you a little bit earlier, where in fact the sort of the classic deepening followed by widening followed by aggradation actually works quite well. So in summary, we can, with such a framework for thinking about how channels respond, we can begin to tease out in the standard manner of channel evolution models the different kinds of responses resulting from the different kinds of typical urban disturbances that we are likely to find on the typical range of urban channels. And really, there's nothing new in how this presents or thinks about these responses. It's really just in a way of organizing what we as geomorphologists already know and already understand, but doing so in a framework that is explicitly developed or crafted or presented, if you will, to for application to the urban stream and watershed settings. Something that has not been quite so, we'll say, typical in the either the scientific or the practitioners' literature up until now. Urban stream studies have been kind of the, we've been late to the party, and we're, I would say, only now catching up to the kind of the level of understanding and of presentation that our colleagues in wildland geomorphology have really enjoyed for some decades already. Okay, let's move on to the spatial dimension of watershed context. And by this, again, I simply mean differences from place to place of different watersheds and the streams that they support, or the streams that they produce. And, for a talk like this, it's much more entertaining to just look at a couple of case studies. And since it's easy for me to pick two streams within a 20-minute drive of where I have lived, we'll do this. We'll start up in the Pacific Northwest on Issaquah Creek. I will take you on a very brief photographic tour of Issaquah Creek. This is out at the south end of Lake Sammamish, one of the two large urban lakes in the greater Seattle area. Lake Sammamish is the smaller of the two, but for those of you not of that region, Microsoft is on the west shores of Lake Sammamish. So here's the Google Earth view looking from the outlet of Issaquah Creek, right there in the lower center behind the word Landsat of image Landsat. And we're kind of looking upstream across the delta through the town of Issaquah and up into the hills that form the headwaters of this channel. And as we take a look at some of the streams up in the headwaters, coming down through the middle reaches, and then down into the area where it meanders through the town of Issaquah, hopefully you get just a little feeling for what this channel looks like and some of the surrounding vegetation and context. Moving down to Santa Paula Creek, a channel of not too dissimilar watershed area and size, and I'll show you a little more about that. Here we have a similar view upstream into the Santa Paula watershed, down there near the bottom, just to the left of the word Google. You'll see the channel pushed through a trapezoidal reach constructed some years ago by the Army Corps before dropping into the Santa Clara River just offstream. The town of Santa Paula sort of sitting over there on the west side of it, and then it also heads back up, or it emerges from its headwater hills. And this is what Santa Paula Creek looks like in some of its headwater areas and moving a bit farther downstream. And the question I would like to pose to you, or have you entertain as you look at these pictures in the next few slides, is this: why are they different? And not so much how are they different, although that's always a useful question, but really why are they different? What does the spatial context in which these streams and their watersheds reside have to do with their differences, the way in which they respond differently to disturbances, and ultimately, I think the goal we are reaching for, although not the one I'm going to get you to today, is how would an understanding of these differences inform or motivate our approaches to stream restoration? I think that's the goal. That's where we're going. But I think we still have a ways before we get there. So let's start by talking about context and, in particular, geology. Many of you know I'm a geologist, so this is always where I like to start. You can see the Issaquah watershed. It's roughly outlined by that little red oval on both maps. And, you know, 16,000 years ago, this landscape looked very, very different. Issaquah Creek at the mouth was probably under about 3,000 feet of continental ice sheet flowing to the south that has imposed substantial imprint on both the, if you will, inherited topography of the watershed, as well as the nature of the fluvial deposits that or the nature of the deposits, the glacial deposits that the river now has to work with, if you will. So we can contrast that to the geologic setting in which Santa Paula Creek resides. I don't have an equivalent map because the before and after, you know, the now and the 16,000 years ago view wouldn't look all that different. But what we do need to understand here is that, you know, the headwaters of Santa Paula Creek are going up at a really remarkable rate. And those of you who are geologists or geomorphologists will look at that number of 1 millimeter per year. It's actually closer to 2 or 3 millimeters per year and say, wow. The rest of you will say, well, that's not so much. But actually, it is. And so we have very young rocks being uplifted into very steep hillsides that are very erodible. And we see lots of field evidence of that all over this landscape that suggests that we have a very dynamic, if you will, source area for sediment delivery into these channels from their watershed. And we can try and quantify that, not so much the direct relationship, but the consequences of those geologic contexts by comparing sediment yields. This was a sediment budget done for Issaquah Creek. You'll see that it actually falls in and somewhat in the lower range of Pacific Northwest watershed studies. This was done by graduate student Aaron Nelson some years ago. And you can see, of course, just while we have the slide up, that if you make a hash of things while cutting down trees on steep slopes, you can generate a lot more sediment than is typical. But if you exert even a modicum of care, we're talking about typical sediment yields that are on the order of 100 to a few hundred tons per square kilometer per year. In contrast, here's Santa Paula Creek. Much of it has not been particularly heavily disturbed by human activity. This is not about the effects of logging on steep slopes. it is simply about the effects of rapid uplift of weak rocks in a steep environment. And in fact, we get sediment yields that are on the order of 40 times, at least at a unit area basis, that which we find coming out of Issaquah Creek. Okay, next, I'm sure all of you are saying, yeah, but what about the rainfall? And so here's the rainfall. Ventura is the closest gauge to rain gauge to Santa Paula Creek. It's actually quite close, maybe half a dozen kilometers or thereabouts. And the Issaquah rain gauge is actually very close to the mouth of Issaquah Creek. So this is a pretty good characterization of at least the monthly averages of rainfall that land on these two watersheds. And as I expect most of you would expect, there's a lot more rain that falls in the Pacific Northwest than it does in California. I mean, that's definitely true now, but it's even true over a multi-decadal long-term average. So looking at just this graph, you might say to yourself, well, if anything, Issaquah Creek has to deal with more water. But in fact, when we start looking at not so much monthly or annual totals, but the intensity of storms that we might expect to be most influential in generating sediment delivery from hillsides, I just picked one off of the rainfall atlas. We could pick any. For those of you who haven't looked at this particular 1963 document, these are in tenths of an inch. Okay, so 70 tenths of an inch is 7 inches for the 100-year 24-hour event. And if we look at the equivalent, and the red circle, it roughly outlines the area of the Issaquah Creek watershed. If we do the same thing for the general outline of the Santa Paula Creek watershed, you actually see values that are on the order of double the rainfall amounts for the equivalent duration and recurrence, and that doubling of rainfall intensity for even moderate as well as large and rare storm events is very typical across the entire spectrum. So even though it doesn't rain a lot in Southern California and the Santa Paula Creek watershed, as they say, when it rains, it pours. So what are the consequences for that? Here are the annual flood peaks for the Issaquah Creek gauge. It's 59 square miles. Remember that number for just a little while longer. And this is kind of the distribution of flows, and the largest flow recorded is up here at about 3,200 CFS 1990. It was truly an epic year for flooding in Western Washington State, as all of us who were living there at the time experienced. Let's look at the same story for Santa Paula Creek, and I'll point out right at the get-go that Santa Paula Creek watershed is actually a little smaller than Issaquah Creek. It's only 42 square miles, but you'll notice that the scale on the left is really different from that of Issaquah. Here is the maximum recorded flow ever seen in a watershed that is, more than 20% larger, and that on an annual basis receives more than twice as much discharge. And yet, when we look at the peak flows, which are generated by the most intense events, we see a very different pattern. And in fact, here's the 2005 flood of record. It's up north of 27,000 CFS, although this requires big error bands because the system really wasn't designed for it. Here's Pete Downs admiring a structure following that 2005 event in the main stem channel. And that's what it looked like actually during not the peak of the 2005 event, but sometime thereafter. Pete had been or will soon be standing right there. But this just gives a flavor, if you will, of the nature of high flows in this watershed. And so this kind of, this, if you will, anecdotal presentation or characterization of watershed differences from in this particular case, a hydrologic perspective, is all very well and good, but if we want to try to apply this more systematically, what kind of a framework can we develop? And I would suggest that there are some frameworks out there, although I will not offer one in particular, but I just want to show you a few examples how, if we wanted to systematize a little bit better our understanding of these kinds of differences, particularly on a climatologic basis, where could we turn to? So one place we can turn to is the work that Laroy Puff did back almost 20 years ago now in analyzing gauge data with respect to a whole suite of hydrologic metrics. And he recognized in work that was first published here in '96, but which has, of course, been developed substantially since then, that we can recognize fundamentally different, if you will, styles of hydrology, and that it is a reasonable assumption, I would suggest, that we may be able, in the fullness of time, to associate particular types of hydrologic response and ultimately geomorphic response, and maybe even ecological response in channels that are residing in one or another of these, I would call them regions, but you can see that they're not entirely spatially contiguous. There is some affinity one with another, but it is by no means perfect. And if you don't like Leroy's arrangement, there are other such categorization. They are broadly similar in their spatial expression and in their overall characterization. But of course, there are always going to be details that differ from one to another. And if a hydrologic gauge by gauge classification is not to your liking, we can certainly turn to ecoregions, which look less to the underlying driver of hydrology and more to what I would suggest is the response to hydrology, namely the ecological communities that evolve. And if level 1 isn't quite detailed enough for you, then we can always move to level 2 and proceed in as detailed and as selective a fashion as we might want for our particular purpose. So as I promised, I was not actually going to answer this question today, but I did want to, if you will, pose the question or pose the premise that we need to think about spatial context. We need to think about it with respect to hydrology, but there are other elements that make different streams different in different places. And at least at the moment, if what we are left with is having to borrow a framework developed for some other purpose, then it will surely not be ideally suited to our purpose, but it may still be better than having no recognized framework at all. So what I'd like to do now, just by way of summary, is to explore, if you will, or just comment on what are the implications of this discussion of spatial and temporal context. So I tried to boil it down to a few short points. The first being that not every channel is able to respond to the disturbance that we think is the most typical or the most commonly associated with watershed urbanization, namely flow increases. That it's not just flow increases that are a source of disturbance and channel response in an urban watershed, but still, it's always a good place to start. That regardless of how you think a channel is going to evolve, and whether you use a formal evolution model or just your own kind of gut feeling based on experience, it's just worth remembering that different contexts are quite likely to produce different or to express different responses, even to the same disturbance. And the last point that I would like to leave you with is one that I think is too often forgotten, particularly by those of us who are geomorphologists or our colleagues in the engineering world who are very much focused on channel form. Um, and that is that if we're serious about restoring urban streams, addressing matters of channel form is, if you will, necessary but not sufficient. And we need always to bring a certain humility of understanding to our work that although studying stream channel geomorphology is really cool, and I have found it fascinating for decades. There's a lot of other things going on in these watersheds, and there's a lot of other problems impacting the condition of these channels, and we really need to be attentive to those as well and not stop until we have understood and restored, if you will, not only the channel form, but also all of the other physical and chemical and biological elements of these systems that we have managed to degrade as a consequence of urban development. So I'd like to acknowledge, at least in writing, the really tremendous number of people that I've had the opportunity to work with over the years and that I trust I will be able to continue working with in the years ahead. Thank you very much.
All right, thank you, Derek. Can folks hear me?
Twice.
Okay. Yes. All right, so that was excellent, Derek, and we've got time for some questions. If folks want to type them in, I'll moderate them. We've already got one to start us off. So, well, here's a big one from Ted and Drenny. Derek, how do you propose that we restore watershed function in urbanized settings?
So the current, we'll say the current paradigm for that is what, depending on what part of the country and world you live in, you would call low impact development or green infrastructure or SUDS or what have you. Essentially, it's an effort at the, we'll say, the distributed landscape scale to recover some fraction or some proportion of the, we'll say, natural, primarily hydrologic processes that this water had before urbanization. Most commonly, what that means is emphasizing stormwater practices that emphasize infiltration, retention, and evapotranspiration. I think the experience that we're beginning to see from both widespread application of these efforts and from some larger scale, longer term evaluations, which I actually think Tim Fletcher is going to talk about next week, um, are that they are moderately, or at least they can be moderately successful. They're certainly a heck of a lot more successful than most of our prior strategies for stormwater management. I think, although the verdict is still out, my bet is that no matter how good a job we wind up doing on restoring watershed function in an urbanized environment, we are never going to take these systems back to a pre-development, pre-disturbance state. And frankly, I think we should stop trying that. I think we should try to understand what are some feasible outcomes using our best understanding of how to get there, and accept the fact that where we either have chosen to or have just by happenstance come to put our cities, um, that we're going to have degraded functions and degraded conditions to some extent. But I think that the greater the emphasis on distributed watershed scale treatments of the land surface, I think the closer we are going to get to a successful outcome.
Let me ask a follow-up to that then. How do your findings, what you showed here about the large range of natural differences among basins, how does that affect our management, or does it just affect the potential outcomes?
Well, I think I would say probably it affects both. Um, I would hope that it would affect the management, and I will say that at least in one little corner here of central coastal California, stormwater regulations have now moved to a spatially explicit characterization of exactly the watershed processes that need, if you will, the greatest attention following development, coupled with a suite of stormwater management practices that are keyed specifically to those watershed processes that are likely to be most impacted. So if you're in an area that is low gradient with very permeable soils, you would probably expect that preserving and recovering infiltration is more critical to the ultimate response of the downstream uh, stream than, say, on a steeper slope with thin soils and that are not very pervious. So I do think that spatial differences absolutely should affect what we do, and I think one of the challenges that we face is that there is a kind of desire for one-size-fits-all approaches to regulation. I worked for a regulatory agency for a while, and I know the appeal of keeping it simple, keeping it uniform, but I think that really compromises our ability to kind of successfully manage these systems.
Okay, thank you. Got a question here from Ann Jefferson. She says green infrastructure practices are focused on hydrology, but as you said, it's not always about changes in discharge. So is there a way to restore, and restores in quotes, sediment fluxes or channel mobility at the watershed scale?
You know, that's a really good question, and the short answer is I do not have an answer to that. I would say that in general, we'll say the starvation of sediment in these high sediment flux systems has rarely been seen as a problem. In fact, it's been seen as a highly desired condition because it's much easier to convey a low sediment laden, it's much easier to convey a flow without much sediment through a constrained urban environment than it is to deal with one that is bulked up with a more typical sediment load. So I think I would have to punt on that one. Uh, if there is a solution, it's going to look a lot like um, moving people back from these channels so that they both have the opportunity to, if you will, recruit sediment um, from their banks, and also room to convey that sediment with all the attendant morphologic and planform shifts that that can create without causing major problems. And I think that's going to be a very difficult nut to crack.
Okay. Um, I've got a question. So last week we heard from Larry Band, who said that showed some evidence that in some of the streams we're looking at in Baltimore, there really isn't much of an increase in discharge. Uh, but the primary change of urbanization to um, it, to the hydrologic cycle is a massive decrease in transpiration, and so they're focusing on increasing transpiration as a management alternative. Um, I was just wondering, in your experience, how widespread have you seen that other places? Is this a potentially widespread way we need to be thinking about it? That we really need to be tackling the fundamental problem in urbanization is a loss of transpiration, or is that perhaps anomalous?
Well, I would hesitate to call it anomalous since we all just bring our idiosyncratic portfolio to any of these problems. I will say that working up and down the West Coast, there really is an awful lot of flow increases with conversion of the landscape. Now, the many of the soils, kind of even on a regional scale, are relatively permeable, and so particularly in the Pacific Northwest, but even farther south, subsurface flow paths are the dominant delivery mechanism, if you will, for getting rainfall from hillsides into stream channels. And the conversion of those flow paths to overland flow is a tremendous alteration of both hydrologic processes and ultimately, sort of stream flow conditions. So I wouldn't want to judge whether, conditions of soil and climate and rainstorms in Baltimore are similar or different. I would just say that people out in the West would love to only have the problem of getting a little more transpiration in their urban watersheds. If that was all we had to deal with, we could already declare victory and go home.
We've got a comment here from Andy Miller, who's assuring us that, in fact, some of the urban streams in Baltimore have extremely high discharge. So
So Andy needs to go
um,
down the hall
I do
and
think
chat
it's
with
interesting. I believe Larry,
Larry.
what Larry was finding in some of the studies, or Larry's colleagues were finding, is real, um, and it does, combined with what you showed us today, Derek, it does actually make me think that we may, in a not too distant future, have a process by which we do examine what's really going on in our urbanized watersheds, understand those the potential changes that have happened, and adjust our management accordingly. If in some places we really do want to focus on increased transpiration, evapotranspiration, as well as trying to decrease the alternation to the surface flows.
Well, I do think that the next step, if you will, for our, we'll say for the practice of our science, or maybe the application of our science, is to develop a more kind of nuanced and granular appreciation um, of uh, of the responses of urban streams to watershed development. I think that, as I said earlier, we are many decades behind the rest of our colleagues in wildland geomorphology in developing first some general principles and then teasing out the nuances and the details and the variety in it. Um, I think we're still largely working from the paradigms that, you know, Leopold and his colleagues in the 1960s set up, and that you can still read about today, and that are to sort of zero order, they're true. But it doesn't mean they're true everywhere, and it doesn't mean they're true in the same way everywhere or at every time. And I think our next step, if you will, needs to be to develop a more nuanced and place and time specific understanding both the drivers of these changes and then ultimately the most effective restoration approaches.
Perfect. Well, that's a good place to end. Thank you very much, Derek, and thank you to all our participants for joining us this week. And I'd like to encourage everyone to come back again next week when we'll hear from Tim Fletcher. All right. Take care.
Great. Thank you very much.